we almost always install the CSP projects with thermal energy storage, because without thermal energy storage, there is no way that CSP can compete with photovoltaics or wind.
In this episode, we'll dive into a really hot topic, literally. By using solar energy, by highly concentrating mirror systems, we can achieve high temperatures from up to 150 to 1500 degrees Celsius. With that kind of heat, we can easily drive power cycles, meaning generating electricity, or even industrial processes like cement production or green hydrogen. The technology generally is known as CSP, concentrating solar power, and typically includes storage to allow for energy supply even when there's no sun available. So this is the very first time we dive into that topic here in the Smarter E podcast in the English version. So I'm really excited about it, and I have loads of questions. For example, how far along is CSP technology? How does it differ from general photovoltaic? And where is the greatest potential? Answers on that in the following minutes, so stay tuned. Welcome to the Smarter E podcast, a podcast for and with the creators of the new energy world. A world in which energy will be renewable, decentralized and digital, bringing together electricity, heat and mobility. Let us show you how we will get there and who will get us there. The expert I'll be talking to in this episode is Wes Stein, a chief research scientist for solar technologies at CSIRO, the Australian National Science Agency. Actually, he's been active in CSP for more than 25 years already and has been instrumental in establishing the National Solar Energy Centre at CSIRO, including building Australia's very first solar tower. More than that, he's also chief technologist for the Australian Solar Thermal Research Institute, and he's the vice chair of the International Energy Agency's SolarPaces Executive Committee. Having said that, welcome, Wes.
Hello, Zach. Thank you for the invitation.
So, Wes, like I said, it's the very first time we're talking about this topic in this episode, so I really start at zero. My knowledge in regards to CSP is almost null. Give me the fundamentals. How does CSP work, and what are the main benefits and differences to general PV?
Well, it's actually a difficult technology to describe purely by audio, and I invite people to go and look up some pictures of it. But essentially, we use arrays of mirrors to track the sun and reflect it and concentrate it onto a receiver. Now, inside that receiver, there's a circulating fluid. That fluid gets very hot, maybe up to 560 degrees Celsius, and it's then stored in a vessel. When required, that heat is discharged to generate steam that runs a fairly conventional steam turbine. Now, the solar collectors can be in a few different configurations. The most common form is like a big trough, about 6 or 7 meters across. And by putting modules together, each of the lengths of those troughs might be 1 kilometre long. That uses a heat transfer oil, and that's heated up to about 400 degrees Celsius. And then the heat's stored in molten salt tanks. Another popular configuration of solar collector is actually based on a solar tower. It's called a central receiver. And instead of using troughs, we use lots of individual mirrors that concentrate the sun up onto a receiver which is on top of a tower. Now, these arrays of mirrors called heliostats could be up to 3 kilometres in diameter, and the tower could be 250 metres high. And on top of that tower is the receiver. The receiver gets hot. Because it's a point focus system instead of a line focus system as with the troughs, it can reach much higher temperatures, maybe 560 degrees Celsius. And again, we use molten salt to store the heat because molten salt's got very good energy density. And that stored heat can then be used at any time of the day or night to generate steam to run a steam turbine. So it's obviously quite different to the photovoltaics that everyone is most familiar with. This is not the sort of technology that's going to go in your backyard or on your roof. They're very big systems. But interestingly, the efficiency of converting a photon of solar energy to an electron of electricity is around about the same for CSP, concentrating solar power, and also for photovoltaics, around about 20%. But of course, the CSP has integrated storage, whereas the PVs don't, and the PVs need an external source of storage, like a battery, for example.
Now, I already have some detailed questions here. First up, because I think our listeners are not all native speakers, so am I. And actually, the word trough, what does that mean?
Imagine a feeding trough for cattle or for cows in a feedlot, a parabola, which in one direction, and a long axis in the other direction.
Okay.
So if you imagine a feeding trough full of water or feed for cattle.
Okay, got it. Perfect. And then also, I mean, I've seen some pictures in the internet, of course, but the sheer scale of it, I was not aware of it. Of course, it's hard to judge distances on a picture, but just you mentioned, you said 1 to 3 kilometers wide around. That's huge.
That's right. Yeah, it's they're very big undertakings, and it's probably one of the reasons why CSP has taken so long to take off compared to photovoltaics and wind, because you can't do small installations. They need to be quite big, and that's determined largely by the steam turbine. Like in a coal-fired or nuclear power station, they generally need to be big because steam turbines like to be big. It's the same with CSP. On the other hand, it gives you great economies of scale if you can build them at large scale.
And you mentioned storage. So, what kind of storage are we talking about? Is it electricity storage or is it heat storage?
It's heat storage, thermal storage. Most commonly today, we use molten salt. So when you take a fairly conventional salt and heat it up past its melting point of about 200 degrees Celsius or so, it actually looks a lot like water, but it's got very high energy density, and it will quite happily go up to about 600 degrees Celsius before it starts to break down. So the hot tank is sitting at about 590 degrees, and the cold tank is above the melting point of about 250 degrees or so. And we transfer when we want to discharge the heat to generate electricity, we move the heat from the hot salt tank to the cold salt tank. And then the next day when the sun comes out, we simply heat up the cold salt tank by passing it through the receiver and heat it back up to 560, 590 degrees Celsius again.
All right, get it. So your peak heat point during the day, that's what you need then during the night. It'll just slowly cool down until the morning and you can heat it up again beyond your 500 degrees Celsius.
Actually, it only loses about 1 degree Celsius per day.
Oh, wow.
So it's very efficient. These tanks might be 30 metres in diameter, maybe 20 metres high. And because of the high volume to surface area, they actually don't lose very much heat at all.
That's interesting because that means if you run the steam turbine, it's basically running almost at exactly the same level day and night. So you don't have any variations.
That's exactly right, and that's the attraction of what we call two-tank molten salt, because the hot tank is always at the same temperature.
So that, I guess, then is one of the main benefits you have in contrast to PV. Are there any other differences or benefits in regard to general PV?
Well, we have a lot more moving parts, of course. Photovoltaics don't have moving parts. So our operation and maintenance cost is generally a little bit higher, but the lifetime of these CSP systems can be up to 30 years. It's really only dictated by the materials that we choose to construct it with.
All right. So I think one of the exciting parts about it is that it's not only an application for electricity production or heat production, but you can actually also use it in industrial processes. So what kind of role can or is CSP already playing in industrial processes?
It's interesting that over many years, many decades, the world's primary energy source has been predominantly thermal. In fact, more than 80% of the world's primary energy comes from a thermal source of heat. So the philosophy of electrify everything, which we often hear these days, is great, but there are always going to be industrial processes that require heat in some form. And in many cases, that heat can be provided by solar thermal. Now, you mentioned some of the industrial processes in your introduction, cement, hydrogen production, for example, but there's also many manufacturing processes such as food and beverage, pulp and paper, petrochemicals, and in Australia in particular, a lot of mining industry, and they operate at a range of different temperatures. So we can tailor the collector type to the required temperature and make it look like a seamless process. It's very important that these industries don't take on board a technology that's going to suddenly cause them to decrease their revenue over time. We want it to be a clean, reliable source of electricity and heat for them. One of the important points to note, though, is that solar thermal provides heat prior to electricity generation, and the efficiency of that heat production is around about 50 or 60%. Now, there are some pundits these days who are talking about using photovoltaics because it's very low cost to generate the heat for industrial processes, but that's only about 20% efficient. So it means that the solar thermal process is around about 2 to 3 times more efficient in terms of land area to produce heat than photovoltaics. So that gives it a very great advantage. There's also these hard to abate sectors such as aviation fuels, and it's possible to use solar thermal to make synthetic fuels that take advantage of the high level of knowledge of combustion machines, but also the very high energy density of combustible fuels. In fact, there's a European project has recently demonstrated the production of green synthetic aviation fuel from a high temperature solar thermal process.
Now, you mentioned earlier that it's so much more efficient in regards to the land use, but let's say I think that you have to probably make several factors match. On the one hand, there's some countries and regions that have the greatest potential as, just generally as sites for CSP. But then, of course, I guess you need it to be close to existing industrial areas and parks. So what does the market look like, and which regions have sort of this perfect overlap of their ideal for CSP, but on the other hand, already they have the industries and the industry sites that need that sort of heat and are actually close to the land you could use for it?
Yeah, it's a good question, and we're working through that at the moment with a number of new projects here in Australia, which I might use just as an example. And there is a large pet food manufacturing company that is presently looking at installing on its existing site, replacing its existing gas-fired boilers because the price of gas has gone so high, with a solar thermal trough collector. And it will be around about 6.5 hectares of these trough collectors combined with storage, which is going to provide the heat for their process. So you're right, you have to be a little bit fortunate to find the combination of solar radiation and land availability to fit these processes. But when you start to dig, it's amazing how many opportunities there really are out there.
So just generally, let's try the different angles. Maybe let's see which countries and regions generally have the greatest potential for CSP. And then after that, we'll look into which countries also happen to have the industrial parks close by enough to actually make use of that potential.
Yeah, so in terms of countries, we obviously look at the Sun Belt, Australia, Chile, many of the African countries are very good. Middle East and Northern Africa regions, the southern parts of Europe are very good. But it's interesting to note that countries like Austria, which typically don't have very high levels of solar radiation, have actually got some of the highest levels of solar thermal collectors in the world, operating breweries for beer production, providing steam for domestic heat. There's a wide variety of countries that can actually use this heat.
And how close do the heat collectors have to be to a production site? Like how much distance can you cover without losing the heat potential?
The bigger the project, the further away they can be, but typically you wouldn't want to be more than a few hundred meters away.
All right, I get that. So it does have to be close to existing industrial parks unless you happen to have the investment capabilities to build up a completely new, let's say, hydrogen fuel facility.
That's right. If it's a greenfield site, then you have opportunities to integrate solar thermal much more easily than you can in a brownfield site.
So what does the current global market look like? Which countries are already tapping into the potential?
Well, at least 20 countries that have got projects at the moment. There's about 100 plants in operation worldwide, that's in commercial operation, which equates to around about 7,000 megawatts electric. Some of those plants have actually been in operation for over 30 years. It's interesting to note that there's a lot of projects being installed at the moment, but China is installing 28 new projects as we speak. The majority of those projects are of the trough design that we spoke about earlier, and about 25% the solar tower design. but the solar towers are starting to take over from the trough projects at the moment. We almost always install the CSP projects with thermal energy storage, because without thermal energy storage, there is no way that CSP can compete with photovoltaics or wind. But there's an interesting trend at the moment to hybridize CSP with photovoltaics, so that on the same area of land you install a photovoltaic project and a CSP project, and you get the benefits of low-cost thermal energy storage from the CSP and the benefit of low-cost electricity from the PV. And that seems to be a really nice trend that's happening around the world at the moment.
That's super interesting. And once again, I guess it's no surprise that China seems to be one of the countries taking a lead there. Now, in regards to future perspectives, how important do you think of a pillar will it be in the future renewables mix, and what's the potential rollout until 2040? At the moment, I think you said we're around 7,000 megawatts or 7 gigawatt. What could we be looking at in 2040?
The IEA, the International Energy Agency, has modelled that by 2040 we could be up to around about 250 gigawatts. Now, given the fact that that's integrating the storage as well, that's got a capacity factor of about 2 to 3 times that of wind or photovoltaics. So that's the equivalent of around about 500 to 800 gigawatts of a variable renewable like wind or photovoltaics. That might seem like a lot. It's a growth rate of about 25% per year, which is significant. But in the past 10 years, we've seen growth rates for CSP of around about 40% per year. So by those measures, 25% per year is readily achievable.
And how do these projects compare cost-wise to other means of energy or heat production, cost-wise, and also in terms of implementation, like the duration you need usually?
When we look at the cost, we like to compare apples with apples, so that we are comparing a CSP project that has storage with another renewable project that also has storage. So when we think about, say photovoltaics or wind, we generally like to think of them integrated with battery power, for example, and they're on a level playing field in terms of cost of dispatchable, firm, renewable electricity.
That is awesome. And I mean, a staggering amount, like adding 250 gigawatts until 2040, that's a significant amount. Now, of course, I guess the technology obviously is ready. It's out there, but I guess you're still researching and having a look at new angles. So what are the hottest R&D insights you can give me straight from your work, from the lab, so to speak? What are you guys working on? What's your industry seeing as the biggest new potential?
The main avenue of research at the moment is a trend towards higher temperatures, because it's based on a thermal cycle, a heat engine, and heat engines will always operate more efficiently at a higher temperature. But at the moment, I mentioned before that molten salt is limited to a temperature of about 590 degrees, and beyond that, it starts to degrade. And so what we're doing is trying to find other materials that can go to higher temperatures. And one interesting option at the moment is based on particles. So if you can imagine a falling curtain of particles, maybe 1 to 3 centimeters thick, and the solar radiation is directed right onto that falling curtain of particles. So the particles get hot up to around about 800 degrees or 900 degrees. The advantage is that they don't freeze, they don't melt, they're very low cost, and the storage is very cheap, because all you need to do is to put the hot particles in a tank. So particles look to be a really exciting avenue of research.
And just for me as a non-science guy, when you say particles, what material is that?
It's a proppant that is actually used in the gas fracking industry. It's like a ceramic particle, and they're around about 200 microns or 0.2 millimeters in diameter. So they're the same particles that are used by the fracking industry to prop open the gas seams so that they can extract natural gas.
All right, thank you. And I interrupted you. You're probably going to add one or the other hot R&D topic there in your list.
The other interesting area is that I mentioned at the start that one of perhaps the Achilles heel of CSP has been that it's always been wedded to a steam turbine. And the industry, and in fact the fossil industry and the nuclear industry as well, is starting to look at using supercritical CO2 turbines. So this is an interesting cycle that's based on the properties of CO2. The CO2 circulates around and around in a big loop, and it's got properties such that the efficiency is around about 20% higher than a steam turbine. And of course, with higher efficiency means lower costs.
All right. So there is still a trend that's generally observable in renewables, that the costs will probably be going down even further. And as you mentioned,
I'd also note the other one,
yeah,
sorry to interrupt, but the other interesting area, which is quite topical, is the use of artificial intelligence. We might have tens of thousands of heliostats which are tracking the sun during the day. And what we've got to do is, especially if the sun is going up and down with clouds coming across, we need to pick which heliostats we're going to use at any point in time, and using artificial intelligence makes a very complex process much more simple. It also means that we've got less than perfect solar energy forecasting 1 or 2 or 7 days ahead. We can use artificial intelligence to look at what the sun is looking like it's going to do, and to increase our revenue production from the CSP project by using artificial intelligence.
do you have estimates of how much you could increase the revenue?
Up to around 10 to 20%.
Oh, well, that's significant. And bear in mind, I guess you said earlier that it's on a level playing field with other means of solar energy production, and that already is one of the cheapest means of energy production out there. So I guess that makes it a really, really interesting technology. Now, thanks a lot for all the insight. That so far already was really like a 101 of concentrating solar power. Now, of course, you're in depth with all that is happening in Australia specifically. What are the perspectives in regards to CSP when it comes to Australia?
I guess every country has its own unique energy challenges, and every country has unique native energy resources to varying degrees. One of the great things about Australia is that it's blessed with an abundant sources of energy, and we've actually always exported more energy than we've used domestically. We've got lots of coal, gas, uranium, solar, wind, and we've even got lots of hydro. Our energy mix has up until now been predominantly black or brown coal, but these plants are due to retire over the next 10 to 15 years. We're also one of the largest exporters of uranium, but we have no nuclear power stations in Australia. It's actually illegal under our present legislation to build a nuclear power station in Australia. But we are the sunniest continent on Earth, and we've got fantastic wind resources as well, with onshore wind yielding 30 to 40% capacity factor. Our government has a legislated target of 82% renewables by 2030, and that's going to require a huge investment in renewable projects and also in the transmission infrastructure that's needed to bring the solar energy from the sunny areas to the coast, which is where most of our population lives. So it's going to need a huge investment in storage, in firm renewables, particularly as we lose the spinning inertia of the coal-fired power stations. A study published just recently concluded that thermal energy storage, as used in CSP, is amongst the lowest cost for medium to long-term duration storage. So if you combine the need for storage with very high levels of solar radiation, it seems to make the prospects of CSP in Australia really good.
That is great news. Now, I also heard that you actually have an exciting conference coming up, the SolarPaces Conference in Sydney in October. I guess those topics will be amongst the ones you'll discuss, but what are your personal highlights when you look at the conference?
We're really excited that the organisation SolarPaces chose Sydney for its 2023 conference. We're looking forward to putting on a great show there. The conference is going to address the questions that we've touched on in this particular interview. We expect over 300 participants, maybe more than 30 countries from around the world. We'll have plenary speakers from government, from industry, we'll have developers, we'll have financiers, and we'll also have research and academics. We anticipate more than 200 presentations on the latest state of the art and the emerging trends in CSP technology. So it's definitely the event that you don't want to miss if you want to learn what's going on in CSP.
And I guess then Australia is also a great continent to travel to have a look at existing projects and sites, CSP sites. So it's worthwhile a trip for sure. Thanks a lot, Wes, for joining me today and really giving me an in-depth run through and update on CSP.
Thank you, Zach. I've appreciated your time.
As Wes already mentioned, more insights on the topic can be found at SolarPaces Conference, taking place from October 10th to 13th, 2023 in Sydney. All information on the program and tickets can be found online at solarpaces-conference.org.